Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling derivatives of logarithms, but one of the things that we're going to need to do this is an exponential derivative that I haven't put in any video yet. So that's what I want to get to first. And that derivative is the derivative of some a to the x, where a is some base. How do we take the derivative of this? Well, the first thing that we're going to do is actually rewrite it completely. A to the x is actually the same thing as e to the x times the natural log of a. Let me explain. First, we can already say that a is equal to e to the natural log of a. And this is just by definition of inverses. E to the natural log of a are undoing each other, and you're just going to be left with a. This is just straight up a definition of inverse situation. If I then raise both sides to the x power, then I'd have e to the natural log of a to the x, but because of how exponent properties work, raising a power like natural log a to another power like x just results in the multiplication of those powers. And so you end up getting e to the natural log a times x, which could be reorganized to be e to the x natural log a. And so that's why we can say that this is just this. That's step number one. Now, if we're taking the derivative of this thing, that's a chain rule situation. The outer function is e to the x, and so we would have e to the x natural log a, right? It's e to the some inner function, the inner function being x natural log a, and so this is just standard chain rule stuff. E to the inner function, because the derivative of e to the x is just e to the x, multiplied by the derivative of the inside, right, which is x natural log a. Well, the natural log of a is a constant, so we can actually bring the natural log of a outside of this derivative just by the derivative of a constant law. So we get e to the x natural log a times this constant times the derivative of x, but the derivative of x is just 1. Okay, so we get e to the x natural log a times the natural log of a, and then you just have to remember that e to the natural log a, that's just a to the x. So the derivative of a to the x is simply a to the x times the natural log of a. Here's just a super quick example. I'm not going to put it in the example section, but if we wanted to take the derivative of 3 to the tangent of x squared minus 1, that would be an application of chain rule stuff here. So you'd get 3 to the tangent x squared minus 1 times the natural log of 3. That's this part, right? Where a in this case is 3, x in this case is the tangent of x squared minus 1. That's why it's going there. But it is chain rule stuff, so then you have to multiply by the derivative of the inside. I just went ahead and put this in parentheses in this step down here, the derivative of the next outer function, right, the next layer, because this is going to be another chain rule situation here. The derivative of tangent is secant squared, so it's secant squared of the new inner function, which is x squared minus 1. Then you have to multiply by the derivative of x squared minus 1, again, standard chain rule stuff. The derivative of x squared minus 1 is 2x, and so here's our derivative. Now, the reason I actually wanted to talk through that is because this gives light to a generalized form of the chain rule specific to exponential functions, right? And it happened right here. The rule we can come up with is if you have a derivative of a, some base a, some constant a, raised to a function, like the tangent of x squared minus 1. In this case, we're generally calling it g of x. Well, by the chain rule, that's a to the g of x times the natural log of a, that's this part here, but then times the derivative of the inside piece, which is g prime. So we're going to come back to this, but that's a general chain rule application that I think that we should know. All right, so now that we got this squared away, let's now look at how we would take the derivative of some log base a function, right, in terms of x. Well, what we're going to do is we're going to let y be equal to the log base a of x, and we're going to rewrite this from logarithmic notation to exponential notation. All right, so what I did is I exponentiated both sides with a base of a. That'll cancel this, right? This is inverse stuff, so that all undoes itself, and you just get the input x. But on the left-hand side, we now have a to the y. And this is why we needed to look at that derivative from before. We're going to implicitly differentiate this thing, which means we need that exponential derivative that we just came up with. This, by the definition of the derivative for a to the x, except that y is some function in terms of x. That's why it requires the chain rule. That's why we're multiplying it by dy dx. That's what we get here. Okay, derivative of x is just 1. If we're trying to solve for this thing that I circled here, then I would have to divide both sides by a to the y natural log of a. A to the y, by the way, is just x, so I'm going to go ahead and replace that with just an x. So this is x natural log a, and again, I'm trying to solve for this. It's being multiplied by this, so we're going to divide both sides now by the x natural log of a. All right, and that's the derivative. The derivative of log base a of x is equal to 1 over x times the natural log of a. Now, this also applies for natural logarithms, and it would be the same, right? Natural log is the same as log base e of x. So if you rewrite that using this thing that we just came up with, the base is e, so you'd have x natural log e, but the natural log of e is just 1, because you have to raise e to the first to get e, so this is just 1 over x, right? That's why this is a different rule. Easier to differentiate natural log of x. All right, so those are the new tools for today. Let's do some examples. All right, example number 1. Differentiate y is equal to the natural log of x squared plus sine of x. So definitely chain rule stuff happening. You have x squared plus sine of x inside of a logarithm. In this case, it's the natural logarithm. The derivative of the natural log is 1 over whatever's inside of it. Whatever was inside of it in this case was x squared plus the sine of x. And then by chain rule, you have to multiply by the derivative of that inside function. So we get this, right? The derivative here, that's power rule stuff. That's just 2x. Sine of x becomes cosine of x when you differentiate it. It's in the numerator position, so I went ahead and just multiplied by the top, and so we're done, right? This is our derivative here. Now, the reason I wanted to do this really quick example is because we already had a generalized chain rule for a to the g of x, and now we're getting one for the natural log of g of x. And this one's actually pretty cool. The derivative of a natural log of some inner function is the derivative of that inner function divided by that inner function. This is a pretty cool shortcut. That means that if you have like the natural log of x squared and you're differentiating this thing, just look at the inner function. It's 2x over x squared. That's it. Right, we're done. Derivative of inside function divided by the inside function, right itself. Example number 2, differentiate y is equal to the natural log of x squared minus 3 cubed divided by x plus 1 squared. So if we want to use the generalized rule that we just came up with, right, this one here, derivative of inside divided by the inside, since it is a natural log, let's do that. If we want to take the derivative of this thing, let's just take the derivative of the inside function, right, that's this thing, so derivative of inside function divided by inside function, right? Again, using the generalized rule, it's just g prime over g when you're taking the natural log of it. Well, notice that this thing here, that is a quotient rule situation. So I wrote a lot of stuff. I want to explain some of it, but I'm not going to do all of it. In general, I'm just using the quotient rule. The quotient rule says you need to take the derivative of the top function and multiply it by the bottom function, but the top function requires the chain rule. Right, it's x squared minus 3 quantity cubed. So I did 3 times x squared minus 3 quantity squared. That's power rule. And then I multiplied by the derivative of x squared minus 3, which is just 2x. And then here I'm multiplying by the bottom, right, the bottom function. I'm subtracting away the derivative of the bottom function, which is also a chain rule situation, but the derivative of the inside function x plus 1 is just 1. That's where that's coming from. Multiplied by the top function. Then you have to divide it all by the bottom function squared, so you'd have x plus 1 squared squared, which becomes x plus 1 to the 4th. Now, what's going on here? Well, here, what I'm doing is I'm using the definition of division for fractions. If we're dividing by this thing, that's the same as multiplying by its reciprocal. So I flipped it, right? This got flipped, and now we're multiplying. Okay, that's everything that happened there. At this point, I've factored out some commonalities, right? I factored out a 2, right? They had a 2 in common. They had an x squared minus 3 squared in common. This one had an x squared minus 3 cubed, so there's still going to be an x squared minus 3 hanging out here, and that's where this comes from. They also had an x plus 1 in common. This one had an x plus 1 squared. We're only taking out one of them because only one of them exists here, so there's still one here, but then it's gone on this one. Okay, nothing happened with the denominator. At this point, though, a whole bunch of stuff cancels. There's an x plus 1 here, so it cancels with one of the x plus 1s there, which is going to make it x plus 1 cubed. But then it's going to cancel with this one. This x plus 1 squared is going to cancel, so you're going to get x plus 1 to the first. That should be 1. There's also an x squared minus 3 squared there's an x squared minus 3 cubed in the denominator, so those will cancel. You're going to be left with one of those in the denominator as well. So we get this just by doing some algebra. This is the derivative. You can simplify it a little bit more. I distributed, combined some like terms, distributed the 2, right? And then this is what I got. 4x squared plus 6x plus 6 divided by x plus 1 times x squared minus 3. And I encourage you to, figure out how to get from here to here to check your answer. But I want to go back to the beginning of this problem real quick. So when we were at the beginning here, this differentiate y is equal to the natural log of stuff. It is a logarithm. Okay, and one of the things that you might remember how to do from long ago is we could apply some logarithmic properties to this thing, some laws of logarithms. Because it's a division inside of a logarithm, you can break that up into two different logarithms that are being subtracted. Because the inputs for each of these logarithms is being raised to a power, you could then apply the power law for logarithms, which says you're allowed to bring that power down in front of the logarithm. And so then we get something that at this point requires only one chain rule. There's no quotient rule involved in it. And furthermore, we're allowed to use that really quick shortcut where you just take the derivative of the inside and divide it by the inside in just two locations. And that's it. So the derivative of this thing, this 3 just hangs out. The derivative of x squared minus 3 is 2x. You divide it by x squared minus 3 because that's the inside function. That's the shortcut. That's the generalized chain rule for logarithms. Here, the 2 hangs out. Derivative of this thing is 1. You divide it by the original thing, which is x plus 1. And then we're basically done. Like, of course, you could find it's not the same answer that we had last time, but you can do some common denominator stuff at this point to figure that out. I'm not going to do it, but it will get us there. So that is something that's actually new. We can use now properties of logarithms to alter the way that this thing looks. Now, in this particular case, I don't know how useful this is. I do think that this is objectively easier, although that's my opinion, so I guess that's a subjective. But my point is that we can actually do stuff with logarithms to manipulate the way that it looks, to get it in a state that's maybe easier to differentiate for you. And I think that's more exemplified in something that looks like this. If we want to differentiate y is equal to x to the 4th times the sine squared of x divided by the square root of x minus 1, this requires, let's look at this. Here is a product rule with a chain rule. It's all embedded inside of a quotient rule. Like, there is a lot of law stuff going on. There's a lot of differential laws that we're going to have to apply to this. But if you instead take the natural log of both sides, you can then break this thing up into a bunch of smaller pieces by using laws of logarithms. Now, you may not remember some laws of logarithms, so you may have to go and research a little bit on what these laws are, but basically anything that's in the numerator is going to be part of a positive logarithm, and then I brought down the power, and they each get their own logarithms. So x to the 4th becomes 4 times the natural log of x. The sine squared of x piece inside the natural log becomes plus 2 natural log sine of x. The square root in the denominator makes it a minus, right? So it's got a negative exponent attached to it. And that is 1/2, because the square root is the same as raising something to the 1/2, times the natural log of its inner piece. None of these pieces at this point require product rule or quotient rule. Yes, there is chain rule that you're going to have to do here, but they're relatively easier chain rule. And more importantly, we can just apply that new generalized property that we have for the generalized chain rule for logarithms. So that's what I would do, right? You differentiate. Now this is also chain rule, right? Because you're taking the derivative with respect to x, so you get y prime over y, right? That's just generalized chain rule, but y is a function of x, so it's implicit differentiation stuff. This just becomes 4 over x, because the derivative natural log of x is 1 over x times 4. This becomes 2 times g prime, sine of x, or cosine of x rather, divided by g, which is sine of x. And I say g just because that's the function we were using in the generalized form. Minus 1/2 times the derivative of x minus 1, which is 1, divided by x minus 1. So this is what we get here. Now, notice the one thing, right? It is cool that we get to break it up like this. We're using log properties. We didn't have to use product rule or quotient rule or anything super crazy like what we would have originally had to do. But we don't have y prime by itself. So there is this extra step. You need to multiply both sides by y to get rid of it here. Y is this. So you can replace y with that thing, and then you're going to get this is our solution. And I would stop here. There's probably a way to simplify this more, but in my opinion, it's not worth it. I'm going to leave it like this. So you have y prime is equal to what y was, which is x to the fourth sine squared x divided by the square root of x minus 1. And then times this derivative that we found implicitly, 4 over x. I turned cosine over sine into cotangent, and then I distributed this 2 here on the bottom. Now this strategy, by the way, has a name. The strategy of taking the log of both sides and then breaking the quotient or product up into a sum or difference of logarithms by bringing the powers out in front, that's a name of a strategy for differentiation, and it's called logarithmic differentiation. And it's useful to solve one of the 4 cases for derivatives involving exponents, which at this point we know how to do 3 of them, right? Derivative of a constant a to the b, that's just 0. The derivative, this right here, I don't know why I didn't name this. This is generalized power rule. It's chain rule stuff, but it's generalized in the sense that you bring down the power, you subtract the power by 1, then you multiply by the derivative of the f of x function. This is the one we just learned. This is generalized chain rule for exponents, for exponential functions. A to the g of x times the natural log of a times the g prime of x. But what are you supposed to do when you have a function, like sine of x or something, that's being raised to another function, like the cosine of x, or something like that? Well, you can use logarithmic differentiation. Here's our last example. Let's say that we have x to the tangent of x. If we change the notation to be a logarithmic one instead of an exponential one like this, what I mean is if we take the natural log of both sides, we get the natural log of y. You'd have the natural log, I'll write this out actually, the natural log of x to the tangent of x, but by a log property you can take this and bring it down in front, so you'd have the tangent of x times the natural log of x. We've simplified the way that we would have to normally take the derivative of this thing. This is significantly easier to differentiate than something like this. And we have to do it implicitly, that's fine, which means at the very end of our problem, because differentiating this is automatically going to give us y prime over y, so we are going to end up having to multiply both sides by y, but luckily we know what y is. Sorry, I'm drawing all over this thing. But let's take the derivative of this thing implicitly first. The derivative of the left becomes y prime over y. The derivative of the right is a product rule situation, so I took the derivative of tangent of x, which is secant squared x, multiplied it by the second function, which is the natural log of x. Then I'm adding the derivative of the natural log of x, which is 1 over x times the tangent of x, and that's why I wrote it as the tangent of x over x. We do need to multiply both sides by y so that we can isolate our derivative, and then replace y with what it is, which is x tangent of x. But then that's it. Right, then we're done. So to differentiate something like f of x raised to another function, g of x, right? We want to differentiate this thing. Use implicit differentiation. Use this logarithmic differentiation idea. Take the natural log of both sides, and then bring down the g of x function such that it's being multiplied by the natural log of your f of x function. All right, so that's it. That main strategy, right? 2 things. We learned generalized chain rule for exponential functions. We learned generalized chain rule for the natural log function. And then we also learned this differentiation strategy called logarithmic differentiation, which is super helpful to differentiate things like functions raised to other functions, or even break up quotients and products into just sums and differences of logarithms, which in and of themselves are pretty easy to differentiate. By the way, you can also use logarithmic differentiation to prove the power rule. Pause the video if you want to take a look. But anyway, hope you guys learned something. If you have any questions, send me an email or drop a comment below. Thanks a ton for watching, and I'll see you in the next one.
And so, once again, the day is saved, thanks to
logarithmic differentiation.